For our last example, we're going to take a look at break-even quantities and how to find them. So suppose that a company's cost function is given by C of x equals 7,000 plus 2x, and a company's revenue function, we have that as 10x minus 0.001x squared for the production and sale of x items. We want to find the smaller break-even quantity. So a break-even quantity is where your business literally, quote-unquote, breaks even. It's the point at which the amount of money that you've made in sales, which is your revenue, is exactly equal to the amount of money that you spent on your costs, C of x. So a break-even quantity is the point at which your revenue is equal to your cost. You might also hear this referred to as an equilibrium point. It's just, again, the place where the revenue is equal to the cost. So I'm going to take my revenue function, set it equal to my cost function, and see if I can solve that equation. So my revenue function, we've got 10x minus 0.001x squared is equal to my cost function, which is 7,000 plus 2x. Now we have a quadratic equation here because our highest power is a 2. I think the easiest way to solve a quadratic equation is to set it equal to 0. I like my leading term to be positive, so I'm going to take the two terms that are on the left-hand side of the equation. I'll add and subtract them and move them over to the right-hand side of the equation. After we do that, we should have 0 is equal to positive 0.001x squared. 2x minus 10x, I should have negative 8x, and then plus 7,000. So here's my quadratic equation. It's set equal to 0. From this point, you have a number of different options about how you're going to solve this. Usually, my first go-to method is to try to factor this. But if you have a coefficient in front of x squared, factoring gets a little bit trickier. You could do it in this case. But instead, I think what I'm going to do is use the quadratic formula, which I'm sure we all remember. But just in case we need a refresher, you can solve a quadratic equation using the quadratic formula, which says x equals opposite of b plus minus square root of b squared minus 4ac all over 2a. And a, b, and c, those are the coefficients of our quadratic equation. So a is the coefficient of our x squared term, b is the coefficient of our x term, and then c is our constant term. So we're going to take these values and plug them into our quadratic equation. So doing that, we should have opposite of b, so opposite negative 8 would be positive 8, plus minus square root of b squared, that's negative 8 squared, minus 4 times a, that's 0.001, times c, that's 7,000. All of that divided by 2a, 2 times 0.001. So we can go ahead and try to solve this equation. So let's see. We're going to take baby steps. 8 plus minus square root of negative 8 squared, I should have 64, minus here 4 times 0.001 times 7,000, I should end up with 28, divided by 0.002. So we end up with 8 plus minus 64 minus 28, I should have 36, all over 0.002. So this is 8 plus minus 6 over 0.002. So we really have two solutions at this point. We've got 8 plus 6 over 0.002, and we have 8 minus 6 divided by 0.002. So let's see. One of my solutions will be 14 over 0.002, which that should give me 7,000. The other solution, let's see, I should have 2 divided by 0.002, and that should give me 1,000. Now, if it asked for both break-even quantities, then okay, we would need them both. But in this particular case, we're only looking for the smaller break-even quantity. So we're only looking for that 1,000. So at 1,000 units manufactured and sold, my revenue is exactly equal to my cost. So that's finding break-even quantities. I think one other cool thing that we can do with it is we can kind of use them to look at a graph and think about what that means for our business. So I'm going to graph a really rough sketch of these two functions. So if I graph my revenue function, I'll do that in black. My revenue function is a parabola which opens upside down. Perhaps it looks something like this. My cost function, I'll do that in blue. It has, say, a positive y-intercept and a positive slope, so perhaps it looks something like this. So what these two break-even quantities that I found, let's say right here at 1,000 and then right here at 7,000, I know that my functions are intersecting because they have the exact same value. That's how we found them. We set them equal to each other. So the number we care about in this particular problem was 1,000. What's also really cool with this graph is I can look at it and say, well, the blue line, that's my cost function. And the black line, that's my revenue function, R of X. And if I look at, I really split this graph up into three parts. First, I'll look at this part here. And really what I want to ask you to think about is which graph is higher, the cost function or the revenue function. So in the part that I've highlighted here, the cost function is higher than the revenue function, which means that I've spent more money than I've made. So if we make anywhere between 0 and 1,000 units, that means that this region we are losing money. So we have a loss in that region. If we move to this region, say between 1,000 and 7,000, now in this case the revenue function is higher than the cost function. The black line is higher than the blue line. So if my revenue function is higher than my cost function, that means that I have made more money than I have spent. So this is good. That means that I've made a profit in this region. So I would like to be in that middle section somewhere because my revenue is higher than my cost, so that means I'm making money. In the last section between 7,000 and beyond, everywhere after that point, again, this time, similar to the first region, the cost function, the blue line, is higher than the revenue function, the black line. So in that case, I have spent more money than I've made. So in that case, once again, here I am losing money. So I'd really like to be somewhere between 1,000 and 7,000 because that means that my business is making a profit.